Institute of Engineering and Technology.
The concept of limit is a complex as well as it is beautiful also. The concept of limit started at the first part of 16th century. It can be seen in the work of Fermat's in the pre-calculus. So in the modern days we are using this concept which was developed in the early 16th century. At that time Fermat was actually developing how to find the optimal values for the small quantities using a special set of conditions known as adequacy for quantities. At that time he was unknowingly using the concept of limit on the quantities, yet the function was not defined. It was Leibniz who developed the idea for derivative, and using that he also developed the concept of dx. Dx means the derivative of function with respect to x. So he was the one who actually originated derivative for the function where x is the independent variable and all rest of the variables are constant. But at the same time Newton was also claiming his work on the concept of limit. He in his work mentioned that the ultimate ratios which he developed was nothing but the prime ratios, which are nothing but the limiting case for the prime ratios. But actually in calculus we got the definition of limit which we are using in the modern mathematics, and it was developed by Weierstrass. He was the first to give the definition of limit in form of epsilon and delta. So today's discussion is around these two main concepts of the calculus, which are actually the first part of the calculus. We are going to discuss limit as well as continuity for the function of one variables. In upcoming lectures we'll see how to extend it for the function of two variables also. So let us start this first part of calculus, which is limit for function of one variable. Now if I consider this concept, it is something like this. I need to take x-axis, y-axis, and if I take a random function y equal to f of x, then if I fix the point x equal to a in the domain of the function, and if I take its value on the function, suppose it is at height L. So the point is AL, and now we want to see how to define limit at this point x equal to a for function f of x. And for that we have two possible ways. We can come from left hand side remaining in the domain towards this point, as well as we can come from the right hand side remaining in the domain at this point x equal to a. Now suppose I start moving from the left hand side, the corresponding points are moving closer and closer to the point of interest AL, and if I take right handed values, then again the points are moving towards AL. Now this is the reference frame which we are going to discuss today very closely. So zooming into that part, it gives us clear idea about how the points are in the surrounding of point x equal to a. So let us go for the mathematical conditions for this limit. If for given epsilon greater than 0, means value of epsilon, it is in the height L. L plus epsilon, L minus epsilon, these are 2 points on the range of the function. If I take these 2 points and its corresponding values on graph of the function, then there exists delta greater than 0 such that a minus delta, a plus delta, they are generating the values of the function such that resulting values are in that part L plus epsilon, L minus epsilon. So if you look very closely what is happening in this particular epsilon delta neighborhood definition, then for given epsilon greater than 0, means for this shaded part we can always find delta greater than 0 such that this yellow part, it generates the value of function from this domain of A, which will assume the value which are in the epsilon neighborhood of value of L. Now, if we shrink this value of L, means if we reduce the value of L, if we can find correspondingly values of delta, we can say that we can move close and close to this point, and after certain values, it will reduce to a value which is very negligible, or you can say almost 0. In that case also, if we can find this interval a minus delta a plus delta, we can say clearly that limit for the function is existing and it is defined on the left hand side as well as on the right hand side by L. So now we can go for the definition which is given by Weierstrass. So if I assume a magnitude of f of x minus L which is less than epsilon, and if I assume 0 less than magnitude of x minus a less than delta. So on these two main intervals, what is happening? So all points in the deleted delta neighborhood of point x equal to a, they are transformed at height which is very close to L in epsilon neighborhood of f of x equal to L. This is what is happening algebraically. Now let us consider the same thing graphically. So all points in the surrounding of x equal to a, they are transformed to very close height at f of x equal to L. So coming again to the same picture, if I take every point which is in the surrounding of x equal to a, it will be transformed at the height which is very much close to L. So if we start moving near to this point x equal to a, either from the left or from right, corresponding points are transformed at height L by rule f of x equal to y. Now here I mentioned that it is almost near. What do we mean by almost near? If I take point x equal to a in the domain and its corresponding points in the neighborhood from the right hand side, they are reflected by these values from the function y equal to f of x, and if I move from the left hand side, the corresponding values are transferred by these points by rule y equal to f of x. Now if I fix the height L by this blue line, and if I take a possible value of epsilon, it will be comparatively bigger. This indicates that the slope of the function in the surrounding of point x equal to a is comparatively higher. That means it is intense slope in the neighborhood of point x equal to a. This will happen and corresponding values of epsilon will be higher in this part. So if the slope of the function is reducing in the surrounding of point x equal to a, the corresponding value of epsilon can be reduced also parallelly. And finally, this is the case where epsilon can be 0. Now this is the case where your graph is nothing but a line which is parallel to x-axis. So this is how the concept of limit is working. Now to understand this on a function, I am assuming a case of y equal to x cube plus 3 and the point of interest is x equal to a. So in this picture you can see clearly that the length, green length, which is nothing but length of epsilon, and the orange length is nothing but length of delta. So we can see clearly in this case, as we reduce the value of epsilon, the corresponding value of delta can be reduced also, which clearly means that for given epsilon greater than 0, we can always find a delta greater than 0 such that all points from that domain a minus delta, a plus delta, points are reflected at height which is always in L plus epsilon to L minus epsilon. So this is the case where limit is existing and they are equal also. Now let me take another case. This is the case where limit is not existing. You can see clearly, if I move closer and closer to the point, there will be a case exactly after this point. You can see the value of epsilon is still not equal to 0, but value of delta is 0. That means there exists value of epsilon greater than 0 such that we cannot find delta greater than 0, for which the function will transform the value into that particular part. This is the reason why left-handed limit and right-handed limit, they are not equal. Now this is the concept of limit. So I hope all of you understand the part which is the first part of calculus, which is limit for a function of one variable. To understand the same thing or the extension of limit, we are going for the continuity. Now in the concept of continuity, we have three fundamental conditions. The first condition is function f of x equal to y, it must be well defined at point x equal to a. Second condition is limit must be existing and it is equal to L. And finally, third condition is both of these previous conditions, they are equal. That means limit is existing as well as it is equal to function's value at point x equal to a. Now let us consider all these three conditions graphically. So the first condition is the function is well defined at point x equal to a. Now what do we mean by well defined at point x equal to a? Well defined means it is finite at point x equal to a. So for the simplicity, I am considering its height f of a like this. Now for the second condition, you can see clearly I am taking point x equal to a and I am taking its limiting value by L. So for this reason, the reflected value is given by a black dot. So that means my value is not exactly assuming input x equal to a, it is remaining in the neighborhood, but it is equal to L. And finally, if I take the third and the main part, that is value of limits as well as value of function, they both are equal and it is equal to f of a and L. So that means there is a complete bridge at this point x equal to a, and so we can say limit is existing at point x equal to a. Now let us take one example, y equal to x cube plus 3, and if you want to check what is happening at point x equal to 0. If we look very closely at point x equal to 0, as we move from the right or from the left, the points are indicated by red and blue colors. They are moving very much closer to the point which is a yellow point, which is nothing but function's value at x equal to 0. So if we consider this part and if we zoom in into this frame, we can see clearly what is happening in the surrounding of this point x equal to 0. We can see very clearly that points are moving very smoothly at this point, which is denoted by yellow color, from left as well as from right. Now the main condition for the continuity which I want to mention is in this frame of reference. If you look clearly, as these 2 points are moving close to the value x equal to 0, there will be a point where this 3 will fall on the same line segment. So that means they are synced by a line segment. If this is happening in any case, we can say that that is the point of continuity. So if you can draw a line segment at least for one subinterval or one interval which is surrounding x equal to a, which contains this blue point, yellow point and red point, we can say clearly that there is a continuity at point x equal to a. So this is the case of continuity. Now let us move to the second part of continuity, which is discontinuity. In which cases we can say that the function is discontinuous. This is the first case. If I take function x upon x minus 1 and if I try to move near the point x equal to 1, we can see clearly there is a vertical asymptote. So the function is undefined at point x equal to a, as well as the left-handed and the right-handed limit both are infinite. In this case particularly they are minus infinity and positive infinity. So this is the case where function is discontinuous and continuity cannot be removed, as my value x equal to a, it falls on a vertical asymptote. This is the second case. Here my function is defined by multi-valued function 1 whenever x is less than or equal to 1, x upon x minus 1 whenever x is greater than 1. Left-handed limit is existing as well as it is equal to 1. Right-handed limit is not existing. It is tending to positive infinity. So function's value is existing, left-handed limit is existing, but right-handed limit is not existing. So we cannot say our function is continuous at this point. Finally, I will take the case where all three are existing. Left-handed limit is existing, right-handed limit is existing, but still the value of the function and the value of limits, they are not matching. So that means still it is discontinuity. And this is the final case of jump discontinuity. If you move from the left, if you move from the right towards the point in the domain x equal to 1, we can see clearly that both limits are equal with value 1, but function is defined at point x equal to 1 by 2. So whenever you will move towards point x equal to 1, particularly at point x equal to 1, your graph will take a finite jump and it will go to height 2 units. So this is a case of jump discontinuity. So I hope all of you understand the idea of limit as well as the idea of continuity for function of one variable. We'll discuss more such topics in our next lecture, where we are going to define derivative for the function of one variable, as well as we'll extend the idea of limit and continuity for function of multi-variables also. Thank you.
LJ Institute of Engineering and Technology.